Hello everyone, welcome back to another episode of Solving LEETCODE Hard Question. Today's question is burst balloons. The question is as follows. You're given n balloons, indexed from 0 to n-1. Each balloon is painted with a number on it represented by an array nums. You're asked to burst all the balloons. If you burst the ith balloon, you get coins, with the value being the product of nums i-1 times nums I times nums I plus 1. In other words, the balloon before it, the current balloon, and the balloon next to it. If i-1 or I plus 1 goes out of bounds of the array, then treat it as if there is a balloon with a 1 painted on it. The question asks us to return the maximum coins you can collect by bursting the balloons wisely. Let's look at the following example where nums is 3, 1, 5, 8. The output is 167. Because the best sequence to burst the balloons is we first burst the balloon with number 1, where we get 3 times 1 times 5, 15 points. Then we burst the balloon with the number 5 on it, and we get 3 times 5 times 8, which is 120 coins. Next, we burst the balloon with number 3 on it, and we get 1 times 3 times 8, 24 points. And last, we burst the balloon with number 8, and we get 8 points. And to total them up, the output is 167. How do we solve this? Pause here if you'd like to think independently for a moment. To rephrase the problem, we want to pick the best sequence that would result in maximum number of coins. So we could try out every possible sequence and calculate the number of coins for each sequence. This will result in a time complexity of O of n factorial. It's a good starting point, but we can do better. With these kind of problems with sequential rules, we can usually try dynamic programming to cache the result of smaller sections and work towards a bigger goal. However, we have another problem. If we pop the current balloon first, it will no longer be the neighbor of the balloons on its left and its right, and this will affect the result of the neighboring sections. A hint to resolve this is to work with the last balloon being popped to avoid dealing with neighbors being affected. So let coins I, j represent the maximum number of coins achieved by bursting balloons between I and j, not including themselves. If we choose index k to be the last balloon to be burst, then we get the coins achieved between I and k, the coins on the right between k and j, and the coins you get by bursting balloon k, which is balloon I times balloon k times balloon j. But how do we know which balloon to pop last? Well, we'll need to try all possibilities and see which one yields the best result. So we'll pick the index that yields the maximum number of coins. And there we have the complete dynamic programming step. Now let's look at the base case. The base case is when I and j are next to each other. In other words, j equals to I plus 1. Since there's nothing in between, and our presumption is that I and j are non-inclusive, we get 0 points in this case. To summarize, here's what we're going to do. We'll initialize a DP array coins with values of zeros. Then, starting with one element between I and j, so coins I plus 2. There's only one possible value for k, which is I plus 1. We'll calculate the maximum coins we can get with the formula mentioned before. And we'll do that for all valid i's. Then we can keep building the array by increasing the length to the full length of the nums array. Here's the pseudocode in Python. One more thing we need to set up is to pad the array with the number ones at the beginning and end, so that when we return coins 0 and -1, it's the maximum number of coins achieved by popping all the balloons between these two elements but not including them. As mentioned before, we first initialize the 2D array with value zeros. Then, for length starting from 2 all the way to the full length of the array, we examine every possible section starting from I to j, and for every possible k, we calculate the value by popping k last. Add that with the maximum number of coins achieved from the left section and right section, and update the maximum result if it's better than what we've already seen so far. In the end, return coins 0 and -1. The final time complexity is O(n) to the power of 3. As we can see, there are 3 for loops here. And the space complexity is O(n) squared because of the 2D array. That's it for today. Let me know if you have any questions, and see you next time.